In this video, we're going to introduce a state machine to handle the different actions our player can perform. A state machine is essentially just a series of states with rules about how to move from one state to another. The primary advantage of using a state machine in our case is that we will eliminate a complex series of if statements that we would need to check our player's state before allowing them to perform certain actions. For instance, if our player is sliding down a wall, we don't want them to be able to duck. If we were not using a state machine, then each frame we would have to check if the player was currently wall sliding using an if statement and then prevent them from ducking based on the result. This creates what is called branching in our code. And for a number of reasons, both aesthetic and technical, this is considered a bad practice. Instead, we can simply put the player into the wall slide state, and then each frame we only have to worry about updating the player's wall slide action. You will notice that at first, the setup for the state machine will seem much more complicated than simply using if statements, but as our number of states grows, this approach will become much cleaner. You might even want to look at the state machine when we're done and try to compare it to the code you would need to implement the same behavior using if statements. You will quickly find a tangled mess with a lot of repeated code, which is one of the best signs that you're doing something wrong when coding. Alright, let's get started by defining a simple struct called input info. This struct will store our player's current input values. We will get these values from the input system that we set up last time. It will have two variables that correspond to the values of our input actions. We are now going to create a script that defines the base class that all of our players' states will inherit from. Let's create a new folder called Player States in our scripts folder, and inside that folder we will create a script called Player State. This will be an abstract class because we are never going to instantiate an instance of this class. It'll simply serve as the template for all of the other states. The first thing the player state needs is a reference to the player, because the states will need to make changes to the player to act as a controller. We are going to define this variable as protected so that the states that inherit from player state will have access to it. We are also going to define a protected variable to hold the player's input info. Now, let's define a constructor for the base class that takes in a reference to the player as a parameter. We will then assign this parameter to our protected variable. We actually want our input info struct to be a Unity component for reasons that we'll see shortly. So let's go back and change it from a struct to a class that inherits from monoBehavior. Now we can use the player reference to grab the input info component, which we will attach to our player in a moment. Let's also fix the capitalization of our player variable because it's customary to use title case for protected variables. Now we can begin defining a series of virtual methods that all of our player states will have access to. We are going to define them as virtual instead of abstract because some states will not need all of these methods. If we define them as virtual and give them an empty body, then the states that inherit from this base class will not need to provide their own implementation. These next methods will be used by the input system to set the input values for our player. In this case, we will provide a body because all of the inherited classes will need to at least set the values. We'll see soon that some of the states need to do more than this, but every state needs to at least do this step. Let's open up our player prefab so that we can attach the input info component to the player. This is why we wanted to define the input info as a monoBehavior component. This way we can view its values easily in the player's inspector to help us debug the player's input. We'll drag it right up below the player script so that it's always easy to see. Now let's open up the player script again so that we can give the player a reference to a player state. We will call this state, and we will define it as an auto property with a public getter and a private setter. This is the beginning of our state machine. We will be able to assign different player states to this property in order to control which state the player is currently in. We'll now create one more script which will define an enum that will hold all of the names of our players' states. We will use these enum values as keys to look up our states. For now, we'll include just the name of the first state that we will build, the move state. We are now going to begin building our first concrete player state. We will first create a new script called move state in our player states folder, and then we will build out the framework for our state machine. The move state class will inherit from player state, so we'll need to define a constructor that takes in the player as a parameter, and then we'll pass on the player to the base class constructor. Now, let's return to the player script so we can begin building the basic foundation of our state machine, which will be managed by the player class. We'll start by including a player state type variable called state type, and then we'll define a dictionary that maps player state types to actual instances of each player state. Let's use the managed start method to instantiate this dictionary. In C#, it's possible to instantiate the members of a dictionary using an object initializer if we put the keys in square brackets. So we'll create an entry for our new move state, and we'll pass the player class to the state using the this keyword, which is a reference to the player class itself. You can see this if you hover over the keyword in Visual Studio. We will now introduce a public method that will let us set the current state of the player. We will call this method setState, and it will take a player state type as its only argument. In this method, we will set the state type variable to equal the type that was passed in, and then we will look up the actual player state in our dictionary in order to set the state property correctly. Finally, we will call the init method of the state we've just switched to, because this is the method that will do any initial setup that the state requires. Let's make use of this new method by setting the player's state to the move state in the start method. Let's introduce an override of the init method into our move state. We do not need to include a call to the base class version of the method because these are just empty methods in the base class. We will come back and add more to this method soon. But right now, let's go back and complete our input system. Remember, we left some comments to remind us of what needed to be added, and now we have the methods in place to finish this class. We can use the player reference to access its state property, and then within that state we have access to the input methods we defined for the player state base class. These methods will allow us to set the appropriate input values for our player's state. We will follow the comments to make the correct call for each condition. Now, we should be able to run the application and see our input info values being updated when we provide input either on the keyboard or the game controller. This is a great time to use the inspector to make sure you've got all of your input actions set up correctly. Now that we have the basic foundation of our state machine up and running, let's introduce a scriptable object that we can use to manage some of the settings and constants that our player controller will need. First, let's create a folder in Resources called Settings. This is where we will put the actual instance of our settings object so that it can be loaded while the game is running. Then we will create a new script called Game Settings that we will use to define the scriptable object class that will allow us to create this settings object. You can think of the script as a template for creating the settings object. For instance, we might want to have a settings object for an easy mode and then create another for a hard mode. We would use this script as a template to create both of these objects, and then we could load the object with the correct settings after the player selected the mode. In order to create this template, our class needs to inherit from scriptable object. There is also an attribute called createAssetMenu that we can apply to the class that lets us define how our scriptable object will show up in the create menu when we go to create an instance of the settings. This attribute has two properties we will set. The first is called FileName, and it defines the default name our instance will have after we create it. And the second is MenuName, which defines the name we will see in the create menu when we go to make a new instance of our settings object. We will now define some of the constant values we will use throughout our game as variables in this scriptable object. Let's start by introducing two values that will control the strength of gravity for our controller. We will define a default value for gravity and then define a stronger value for gravity when the player is falling. Now, let's return to Unity and create an instance of our scriptable object. Remember to create it inside the settings folder that we made earlier. You will now find Game Settings as an option at the top of the Create menu. If you select the new object, you can see fields where we can edit the values we defined. Let's now go back to our player script and introduce some references to the different components we will need. We will define a reference to the animator component, a reference to hold the player's main collider, and a reference to its rigid body. Then we'll jump down to the Managed Awake method and we'll gather all of these resources in the usual way. All three of these components are attached directly to the player object, so we only need to use getComponent with the correct template parameters. Next, we will define a reference to the game settings object we just created using our scriptable object. Since this is a resource, we can load it by using a static method in the resource class called load, which takes a template parameter. We then provide the path to our file starting at the root of our resources folder. We are now going to extend the constructor of our player state by also passing in the game settings object. These states are not Unity components, so in order to give them easy access to the game settings, we will simply pass in the object when we construct them. After adding the reference to the player state base class, also be sure to update the move state class so its constructor has the right signature, and then go back to the player script so that we can supply the settings object while we construct the move state for the dictionary. We are now going to introduce some properties and methods that will allow us to update different aspects of our player. We will start by defining a property that returns the transform's position and another that returns the rigid body's velocity. We will then write two methods to set the position of the player. The first will take the x and y components separately and then use them to update the transform position, and the second will simply be a convenience method that takes in the position as a vector 2 and then separates its two components and calls the first setPosition method. This is a practice I often follow because in different scenarios they can both be helpful. We will also follow the exact same process to write methods to set the rigid body's velocity. And finally, we will create another method to update the rigid body's gravity scale. This is the strength of gravity for the player's rigid body. We will now include some methods to control the animation for the player. We will define one method that takes in the animation state name and uses it to play that animation. And then we will define a second method that allows us to set the speed at which the animation plays. Whenever we set a new animation to play, we will also reset the speed back to 1, which is the default speed. Then we will use the animator reference to call the play method. In order to get the correct full state name for the animation, let's look at the animator window for our player prefab. We can see the clip names listed on each animation block, and then we can see the animation layer name listed in the panel on the left. To create the full state name, we will need to combine both these. We are going to build the state name using string interpolation. We can start an interpolated string by placing the $sign right before the string. We start the state name with the layer name, then we put a dot before including the full clip name. Since all of these animations will begin with player hyphen, we will also include that before we interpolate the particular state name into the string using curly brackets. I'll use a comment quickly to demonstrate what the final product will look like after interpolation for the idle animation. That completes our setup for the state machine. We now have a fully functional player state class that will allow us to build out the other concrete states. And we also have a number of methods on our player class that will allow the states to control the player. In the next video, we will finally put our first state into action by completing our work on the move state.